All right. So before we get into this problem, we have to understand what's happening. Because if you don't understand what's happening and you're just trying to use some equations that you learned, you're not going to know how to use those equations. So let's describe the physical process. It's not a chemical process, right? Because we're just dropping one hot thing into a cold thing, exchanging heat. It's a physical process. So what is happening when I drop this hot piece of nickel metal into a cooler, not a solution, a cooler cup of water? So temperature moves from hot to cold, right? So the metal, the nickel, is going to lose heat, and that heat that's lost by the nickel is going to be equal to the heat gained by the water, right? So the heat, which is Q, the negative heat lost by the nickel, is equal to the positive heat gained by the water. This idea has to make sense in order for you to solve this problem. Okay. From there, we don't know the heats though, right? We don't know Q. Agree or disagree? Agree. Because we know Q is equal to MC and then delta T, which is final temperature minus initial temperature, right? But we don't have a final temperature, so therefore we don't know the Q. But what we do know is what I just stated, is that Q equals this. So we can plug that red part into both sides, where we get negative MC delta T of the metal and it is equal to the positive MC delta T of the water. Do we agree here? Yeah. So we also just said that delta T equals the final temperature minus the initial temperature. So therefore, negative MC T final minus T initial of the metal is equal to the mass of the water times the specific heat of the water and times the change in temperature, which we said is T final minus T initial of the H2O, right? So let me highlight this so we can see. What do we know about these two numbers here? Or these two, those variables, T final. This is the final temperature of the metal, and this is the final temperature of the water. Are they going to be different or the same?
Yeah, the same, because they have to both be his final temperature.
Yeah, we can't, but gotta let them go into the trenches first before I pull them out, okay? So the T final is gonna be the same, right? Because eventually at some point, all the heat gets lost from the metal and goes into the water, and therefore they become the same temperature, right? So if you take put a hot pan into your sink that's full of water, eventually it's going to come up to some temperature. The water will raise to a temperature, the pan will lower to a temperature, but they eventually end up at the same temperature, right? You're not going to have one be higher than the other. So therefore, those variables are the same, which means we can solve algebraically for T final. And when you do that, you actually get this equation. T final is equal to M1 C1, the initial of one of them, plus M2 C2 T2 over M1 C1 plus M2 C2. In this case, it doesn't matter which one or two is. Let's just say one is the water. Or I could have easily said two is the water. And let's just say two is the nickel. So you have to just make sure that when you fill in this equation, everything that has a 2 is all the information for nickel, if that's what you assigned it to. So both in the numerator and the denominator, everything that's a 1, it's the water. If you assigned water to be number 1, or I could have easily done 1 is nickel and 2 is water. Okay, it doesn't matter. Have to be consistent because you can't multiply the mass of water times the specific heat of nickel, right? That you can't do that. So instead of doing all the math to isolate for this variable, I just told everyone on Wednesday, memorize this equation, which when you think about it, not too bad of a equation or too hard of an equation to memorize, because what is it? It's the same thing, M1C1, M1C1, M2C2, M2C2. They're the same thing, except on the numerator, we have the temperature. So the T goes on top, okay? So if you're given a problem that asks you to solve for the final temperature, given, it's only in specific problems when you have a temperature of, or one species being dumped into another species and they equilibrate at a different temperature, okay? So this is an equation you can use to solve these kinds of problems. So if you use that equation, what did y'all get as your answer? Ask yourself, does the specific heat of water being 0 make any sense? Because then water would just be boiling when you take it out of the fridge. What is the specific heat of water? Because this is something you have to know.
4.184.
Yeah, 4.184, 4.1839 maybe. I don't know what you were gonna say next, but yeah. So that's the specific heat of water. And Nicholas, that is something we have to know. You're never gonna be given the water because it's gonna be assumed that you know the specific heat of water, okay? So what did y'all get using this equation to solve for the final temperature? See, back in the day, when I took this class, I was like, oh my God, I had a problem like this on Alex, and I was like, I'm never gonna derive this thing again. I'm just gonna memorize the equation. So I mean, you can choose to memorize it and save a couple minutes on the test, or you can just do all the math and have to worry about negative signs and everything, and maybe get the wrong answer at the end of it. Whichever one you want. So, anyone get an answer yet? 21.4. Anyone else get a different answer? Got the same? E final equals 21.4. So water has such a high specific heat, it's 4.184 in comparison to the nickel, which is why even if you dump a piece of nickel at 260 degrees Celsius into that water, it's only going to change the temperature of the water just by a little bit, because the nickel will change its temperature so easily because of its low specific heat. Whereas the water takes more energy to change its temperature. So that's why we only see a change in temperature for the water of 1.4 degrees Celsius. So yeah, the answer makes sense, right? Any questions? All right. You want me to stay on the screen for a second, or are we all good? All right, I'm gonna assume we're good then, since no one told me to stay on this screen. And I will let Rish do the next one. You want to do the next one, Rish? Alrighty.
Right. The heat capacity of a bomb calorimeter, remember that? was determined by burning 6.79 grams of methane, energy of combustion, negative 802 kilojoules per mole, CH4 in the bottom. Temperature changed by 10.8 degrees Celsius. What is the heat capacity of the bomb? Great question, right?
I don't think they've gone over this, so you might have to.
Raise your hand if y'all have no clue what is going on with this problem. Absolutely, no idea whatsoever.
I will try, guys. If you're gonna be wrong, you might as well be confident.
I mean, I guess we first have to find the moles of. Thing.
Good guess. Is it right? Probably is. But yeah,
Wait, I see always in joules.
in this case, the heat capacity would be in a particular set of units. That is joules per degree Celsius. Or the grams is for specific heat capacity.
I'm just.
Raise your hand if y'all want me to just to go over it, because y'all haven't seen it before. Yeah. All right. So, calorimetry, right, is the name of the game here. So, y'all learned about coffee cup calorimetry, right? That was just take say this is my coffee cup. You fill it with water, and then you put a reaction in it, right? Very, very nice drawing, I know, but a bomb calorimeter is sort of the same thing. So you're gonna take let's say this is our bomb, our reaction vessel, and you're gonna do a reaction in it. But the only thing here, in the coffee cup calorimetry, did you have to take into account the heat from the calorimeter at all? No, right? Because we were told to ignore it. But the thing is, with the bomb calorimeter, it's not that simple. So with the bomb calorimeter, you have to take into account the heat capacity of the calorimeter. So the heat capacity of the calorimeter has to be taken into account. What was the equation we used for a coffee cup calorimetry? MC delta T, right? But in this case, can we use that same equation? Because we have to take into account the bomb calorimetry. No, so I'm gonna introduce y'all to a new equation. Q of the calorimeter equals P of the calorimeter times delta T. And as Colin asked before, he asked if the heat capacity units were joules per gram times degree Celsius as they were in the coffee cup. And the answer to that is no, right? Because here it has to be in joules per degree Celsius. Because we multiply by Celsius on top, Celsius cancels, and we're left with joules, which is what we want for Q. That being said, right? Bomb calorimeter, we have this new equation laid out for us. Now it's just a matter of using it. So heat capacity was determined by burning 6.79 grams of methane. We're given a heat of combustion, which is nice. We might need that. The temperature changed by 10.8 degrees Celsius. All right. So what is the first step here?
Change temperature.
Grams of methane.
Grams of methane to moles of methane. That's exactly right. So 6.79 grams of methane. Methane is CH4. You didn't know. Molar mass of that is 16.01. 16.01 grams for every 1 mole. All right, now we're in moles of methane. How do we get from, or where do we have to go next? Kilojoules. How do I get from moles to kilojoules? Yeah, you use the heat of combustion in this case, right? So, this heat of combustion, another way to say it is this, it's the delta H. So the delta H, right, we're given is negative 802 kilojoules per mole. And then we can use that to find the overall heat released. So I can say that for every 1 mole of CH4 I have, I'm gonna release 802 kilojoules of heat. And of course I said, it says determine the heat capacity, right, of the calorimeter. What I'm gonna do is I'm gonna change these kilojoules to, the 1 kilojoule here is equal to 1,000. All right, and then it's just a matter, right, of plugging things into your calculator. Should get negative 340,136.16. All right. Now this is our what? What did I just find?
The
Q. That's exactly right. Found my Q. So this is equal to my Q of reaction. Thing was with bomb or with coffee cup, right? We said Q of the water is equal to what? And negative Q of the reaction. So in this case, same thing. But instead of the water now, we're using the calorimeter. So Q of the calorimeter equals negative Q of the reaction. But here we've already solved for negative Q of reaction. Because all the negative is saying, right, is that we're releasing heat, which in this case we are doing because delta H, right, is negative. And a negative delta H means the reaction is what? Exothermic, releases heat. So now it's just a matter of using our good old equation. So QCal equals Ccal times delta T. So the heat capacity of the calorimeter will be equal to Q of reaction, in this case, divided by delta T. So our negative Q of reaction. Because remember, Q of the calorimeter equals negative Q of reaction. So all I did here was I substituted Q of the calorimeter with negative Q of the reaction. They're the same thing. So what we do here is say that negative times negative 340,136.16 divided by our 10.8. And you do this because the change in temperature is 10.8. So you get a delta T, or sorry, not delta T, heat capacity of 31,494 joules per degree Celsius. Does this make sense? Or does this answer make sense, I should say? Yes, it does. Yeah. The number makes sense, right? Because the heat capacity should be what? Positive or negative? Always. Heat capacity is always positive till the day you die. So, yeah, this is how you find the heat capacity of a bomb calorimeter. Any questions on that? Yeah. Sure. So, bomb calorimeter, right? Basically, it's like a coffee cup, except you have to take into account Q of the calorimeter. That's just a feature of the calorimeter, per se. So we have this new fancy equation. Q of the calorimeter equals the specific heat of the calorimeter times delta T. And in coffee cup, we said that the Q of the water equals negative Q of the reaction. Sort of the same here. Q of the calorimeter now equals negative Q of the reaction. Excuse me. So In order to find our heat capacity, right? We first have to find Q. So to find Q, that's what this whole process was for. So we're gonna take our grams of methane, right? Grams of methane, we convert it to moles. And then our Q, right? What units is Q in again? Kilojoules. So we needed our kilojoules, but we want joules in this case, since the heat capacity is always in joules. So we take our grams, convert it to moles. Then they gave us a heat of combustion here. We're going to use that heat of combustion to get from moles to kilojoules. That's our conversion factor here. So we get an amount of kilojoules. Then we're going to convert the kilojoules to joules. So we get our final answer of, in this case, negative 340,136.16. This is how many joules of heat. So this is our Q of reaction. So it's saying that the reaction that we did, right, in this bomb calorimeter, in this case, the combustion of methane reacting with oxygen, it released 340,000, or this meant this much joules. But now it's not asking for the joules, it's asking for the heat capacity. Now we're going to use this equation right here. Q of the calorimeter, C of the calorimeter times delta T. Except we know that the Q of the calorimeter equal to the negative Q of reaction. So it's the same like calorimetry principle in coffee cup. So we've input a negative here. So negative times 340.136.16. Because again, this is Q of the calorimeter. So Q of the calorimeter would have an opposite sign from Q of the reaction. That's why that other negative is there. So then we're going to divide this by our delta T, which in this case it says 10.8. Temperature change by 10.8 degrees Celsius. And we got our final answer of this, 31,494 joules per degree Celsius. That makes sense. Right. Any more questions on that? Right. This is sort of a related problem, not really. Same principle. 1.6 gram sample of acetylene produces a temperature rise of 16.9 degrees Celsius in the same calorimeter. What is the energy of combustion of acetylene in kilojoules per mole? I'll give you all a bit to work on this, like two minutes.
When you say in the same calorimeter, does that mean you have to take into account the methane? If it's in the same calorimeter.
No, this is like a different reaction. So in the previous problem, we did a combustion reaction with methane. This time we're doing it with acetylene.
Twenty seconds. And time. Okay. So. See a couple blank faces out there. I'm gonna call each one out. No, I'm just kidding. I'm just kidding. So this is a part A and B type of question. On a test, you're not gonna have part A and B. And on the test, actually, I'll explain to you that after we finish this part, okay? So a 12.6 gram of acetylene produced a temperature rise of 16.9. What do we always say when we start getting these things? A temperature rise of 16.9 is a delta T, right? In the same calorimeter. If it's telling us the same calorimeter, what that's telling us is that the heat capacity that we found in part A applies to the same calorimeter, all right? So this tells us that C cal is equal to the 31,494, but I'm just gonna abbreviate or change that to scientific notation and round a little bit. So 3.15 times 10 to the fourth.
Rich, it was same.
Yeah, it was the same vessel, but different reaction. That's what I was trying to get at.
All right. So are y'all with me so far? So it's asking, and then it says, what is the energy of combustion of acetylene in kilojoules per mole? So we have to understand what this question is telling us and what it's asking of us, right? So first it said a 12.6 gram sample of acetylene. So that's telling us a mass, grams, and we know from mass we can get moles, right? So that checks out. That's all good there. Now, what is the energy of combustion? What is the variable that we're wanting to solve for?
Kilojoules over moles.
Kilojoules per mole, but specifically, what is that? Like that heat, or is that temperature?
That's the Q of the reaction.
Yeah, so it's delta H, which is the enthalpy. So enthalpy is, there's a lot of different ways you can say it. Sometimes they'll just say, what is the enthalpy of the reaction? Sometimes they'll say, what is the energy of combustion of acetylene? But every time you see kilojoules per mole, you should start thinking of this variable right here, which is equal to the Q of reaction divided by the moles of whatever. So in this case, it's asking for acetylene, so it would be moles of acetylene. So we start connecting some of these dots here. Moles of acetylene is going to be found using this portion right over here, okay? See that? But how are we going to get Q of reaction?
We have it. This is just the Q cal positive, negative.
Q cal what? It's because remember, this is a different thing. Originally it was asking for methane, 6.79 gram sample of methane, and now it's asking for acetylene with a 12.6 gram sample. So you can't use the same Q of reaction from part A. Okay. So let's do what Rich said. The principle that we do know of a bomb calorimeter is that the energy released by the reaction. Let's do this in blue. Negative heat released by the reaction is equal to the positive heat gained by the what? In this case.
Acetyl.
Now the acetylene reacting, so that's the reaction. So what is absorbing the heat?
Calorimeter.
The calorimeter. So Q of the cal, Q cal, right? And we are interested in which of these variables?
Reaction.
Reaction, right? Because we see what we're trying to solve for over here, delta H, and delta H is Q of reaction over the moles. We already identified moles comes from this red highlighted part over here. And we're going to solve for Q of reaction so that way we can eventually, our end goal is to put Q of reaction and moles in that last equation, and that'll give us our answer. So how are we going to solve for Q reaction? But first, obviously, we need to just isolate for Q reaction, not negative Q reaction. So if we multiply both sides by -1, we get Q reaction equals negative Q of the calorimeter. And what do we know the Q of the calorimeter is equal to? What's our equation for Q, the heat associated with the calorimeter?
The concentration of the calorimeter times temperature.
Yeah, so Q cal equals E cal times the change in temperature of the calorimeter, right? So if we plug this part in for this part, then we would get Q of the reaction equals negative C, the calorimeter, times delta T. Which of those variables do we have already? You're given delta T in the problem, and earlier we solved for C cal. So earlier we solved for C cal, which is the heat capacity of the calorimeter. And that's one of those variables right here. And then we were given in the problem delta T, right? Which is right here. So this is why I say identify the things that you're given in a problem as you're reading it. So that way you know what you have and what you don't have. And you could even, I've seen people, make a checkbox where they put no here. They write all the information that they know here. So they write delta T mass, which can get them to moles. And then we know that the C cal was from the previous part A, right? So that's one way to do it to help you solve problems, is writing what you know and what you don't, and then write what you don't know on another side. So can we solve for cube reaction? Yeah, right. So go one step down, cube reaction equals negative, plug all the numbers that we have in now. So 3.15 times 10 to the 4th joules per degree Celsius times the change in temperature of 16.9. 16.9 degrees Celsius. This gets us a Q of reaction of approximately negative 532,350 joules. That's our answer, right? No, it's not. What are we looking for? What do we establish what we are solving for? Delta H, which is what?
Reaction over moles.
So the units for delta H is kilojoules per mole, but what is delta H?
Well, it's combustion, the energy of combustion.
Energy of combustion, which is also known as the enthalpy, right? So we're just looking for enthalpy. So yes, we did all this work, but we're still not done yet. Let me go ahead and block this area off. So all we have to do now, have our delta H equation, which we said is equal to Q of reaction divided by the moles of acetylene. We know Q of reaction equals, so it equals negative 532,350 joules, right? But we want this in kilojoules per mole, so we have to go from joules to kilojoules. So we would get negative 532.350 kilojoules. Divide this by the moles of acetylene. But we already identified how to get moles of acetylene, right? 12.6 grams of acetylene, so C2H2. Divided by the molar mass of 26. 26.02 in my book. And this gives us moles of acetylene of 0.484 moles C2H2. Which is then that's exactly what we need. So then we plug that into our equation. 0.484 moles of C2H2. And if we do all this good stuff, we should get a heat of combustion, which is delta H of negative 1099.9 kilojoules per mole of acetylene, C2H2. Okay, that's our answer, right? So take a second and then take a second to just process this, and I will explain to you what I wanted to explain earlier about this kind of problem. If there's any questions, you can ask them now. David, why were you late? I better laugh.
You know, or you ever just subconsciously fact that you don't even remember too much.
No?
I did that, so I turned around to make sure.
Okay.
You gotta be sure.
Was it locked? Oh, okay, okay.
That's subconscious.
Yeah.
But I was in the car, like, I locked my door.
What if I can like subconsciously open it?
What? All right, any questions on this?
Hey, they call me telekinesis for a reason.
Yeah, yeah.
I like my car door like 5 times.
Why did I multiply it by what again? So it's just to show how, honestly, I just get rid of the negative on this side, because we're solving for a cube reaction, not the negative cube reaction. So I isolated the cube reaction just by multiplying both sides by -1, right? So that'll cancel out the negative here, and that'll make this a negative. Yeah, honestly, you don't have to show this step. I just do it because when I made the key for this, I wanted people to be able to like understand what's going on without me being there explaining it to them. Well, if we didn't include this negative, if we didn't bring this negative over to this side, then what we would have solved for at the very end was negative cube reaction, and this would be a positive value. That doesn't make sense, right? If we didn't move the negative over here. So have to move the negative over there so that way we get the right answer, because it would be negative cube reaction equals 532, but we don't need that. We need cube reaction, not negative cube reaction, right? That makes sense? Are there any other questions? So the thing about this problem is that it's actually, what you'll see on the test is all the information at the top, 63, and then this part here. And you'll be asked the same question. So they're not going to give you this part where they tell you to calculate the heat capacity of the bomb calorimeter. That's going to be expected for you to know that you have to solve for that, okay? So I kind of guided y'all in the right direction if you were to do this by yourself by asking you to solve for this first, so then you can do part B. But on the test, you're not going to be given this step right here. You're just going to be given that information, this information, and asked what is delta H. And you would have to know that you have to do this first and then do this part. Okay, so that's how you're going to see it on a test. So just know that's, yeah. So, yeah.
Maybe like
Any
one
questions
question
about that?
less one.
Yeah, I know. I might have made it too easy by a step by things, but you know, step by step, but trying to help. I'm trying to teach y'all. I'm not trying to. Are there any questions? How many of y'all don't understand this? Okay. You have any questions or?
She doesn't understand, she can't ask questions.
So I would want to do 64 because it's the same thing, but then that wouldn't give y'all any good practice questions to do on your own time, so I'll let y'all decide. Do you want me to go over 64, or do you want me to send out the key for 64 and y'all can try to do it on your own?
Not the key.
Okay. All right, Rich, you gotta send out the key.
I gotta send out the key.
All right. Is there any other like topics y'all wanna go over?
Yeah, I have a question. Said for B.
Mhm. So it would say like, what is the final temperature? Or maybe it'll say it started at 6.9 degrees Celsius. But because it says the temperature rise 16.9 or rose 16.9 degrees Celsius, that's telling us a delta T. It doesn't matter about initial or final, it's just saying it changed 16.9 degrees Celsius. Yeah. Any other questions? Ask them now, or
Forever hold your peace.
yeah.
I'm still gonna roll.
Okay. So every single one of y'all is gonna get this right on these. All right, like to see it. And wow, that's actually 65 is the last question we have on this review. I think there might be some other ones. Oh yeah, never mind. We skipped a lot because I don't think most classes have gone over Hess's law yet.
Have y'all gone over it now? Still don't know. what I'm talking about.
You just like flip it a little bit.
Yeah,
Alright.
You do flip it.
How small can you make it?
Pretty small. Yes, anyways, what do y'all wanna? The thing about going over a new topic right now, like Hess's law, is,
Will this be on the test?
yeah, this is definitely gonna be on the test. The thing about going over it right now, I guess we could do one problem. And then the rest we can save for Monday, all right? And then I want Wednesday and Friday to be days where bring your own problems and work on them, help you out, okay? And maybe we can do a couple problems together.
Like a therapy session?
Yeah, kind of like a therapy session. That's what I want on Monday and Wednesday, just because everyone's on different, going at a different pace. There's gonna be some people that are ahead, some people are behind, and I want to be able to help everyone, so. We'll do question 51, and we're gonna have to teach them a little bit about what Hess's law.
That 1/2 to 2.
You're reading that right
Oh,
now.
half oxygen.
Yes.
I never missed.
Okay, never.
There's no base equation. Where it's like, this equation, here's the two. Oh,
Yeah.
Worry about it.
Oh, no, that's fine. Oh, there, see, it's at the top, I just couldn't see it. Right there.
Oh, yeah.
Yeah, that's what I meant, cause I was just looking at the two equations, like, what am I supposed to?
Wait, where did two come from then?
Equation, well, like, that equation.
Oh, I thought you said two, like.
Oh, no.
I understand this.
Well, you will by the end of today. I'll guarantee that. All right, raise your hand if you have absolutely no clue what's going on.
Or I'm too busy writing.
you have a clue of what's going on? Alright, I'll take that as I need to go over it. Alright, so Hess's law. H-E. Double S. Apostrophe S. Law. I know how you spell that, but I don't care. Alright, so here's the thing. This law is used to find the delta H of a reaction overall. The idea here is that the delta H of the total reaction is equal to like the sum of the delta H of its parts. You know what I'm saying? Like a total reaction will be the sum of its parts. So in a lot of these, right, delta H problems, there'll be this thing called a goal equation. So our goal equation is basically what we're trying to achieve at the end of the day. So they'll usually give you a goal equation and like 2 to 4 like other equations. Really could be an infinite amount, but like 2 to 4 like equations, right? And the main point of these problems is you have to flip and manipulate these equations, right? These equations at the bottom to make that equation.
Okay.
So the whole point is you want to make this equation. But there are certain rules you have to follow to do this. So right off the bat, I'm explaining some of this. So first and foremost, right? Let's look at what we have in our goal. So we have a calcium here on our reactant side. We have 1/2 oxygen on our reactant side again. We have carbon dioxide on our reactant side, and we're trying to make calcium carbonate. All right. So let's look at our equations we have. Here's one with calcium and oxygen on the reactant side. There's this weird calcium oxide thing, but we'll worry about that later. We have, oh wait, is calcium carbonate supposed to be on the reactant side? No, right? What side should it be on? Products. So do y'all agree with me that we have to flip the equation?
Yeah.
We gotta flip the equation here. So this would be instead CaO solid plus CO2 gives us CaCO3. We just flip the equation, right? What happens to the delta H?
It flips to negative.
Flips to negative. We have to change the sign. Anytime you flip an equation, you have to change its sign. So the 178.3 becomes a negative 178.3. Anytime you flip an equation, flip the delta H. All right. So now, can we make our goal equation now? Is everything like on the correct side? It should be there. How do we get from what we have right now to our goal equation?
Yeah, them together.
So if we add them together, what happens?
At the top. I mean, I suppose you need to write the net ionic equation for it. It'll basically cancel out to the top.
I mean, not really that ionic equation, but okay. What I was trying to get at is, what do we need to cancel to get to our goal equation? Calcium oxide. So goodbye, good riddance. Now, this is our goal equation, right? If we add this all out, it's Ca solid plus 1/2 O2 gas. 1/2 O2 gas gives us CaCO3 solid. All right. Now, what do we do with the delta H's?
I'm gonna see.
Add them together.
Oh, my bad. Yeah, I forgot to include it, but yeah, it should be on the reactant side. Good catch.
Plus CO2 equals.
Plus CO2 gas equals CaCO3. All right, now what do you do with the delta H's?
Add them together.
Add them together. So this is a negative 635.1 plus a negative 178.3. So what are we gonna get?
Negative 813.
Negative 813.4. And what are our units?
Kilojoules.
Kilojoules. That's it. All I need to do. This is Hess's law.
It's not that bad. I just don't like the other one.
All right, the goal, the main goal here, right? This is sort of an easier problem. Main goal you want to do is always try to make your goal equation. Flip or manipulate, do whatever you need to do, get your goal equation. Only things you're allowed to do, by the way, is flip the equation and multiply. Like you can't divide by anything, you can't like subtract it. Just flip, multiply, that's it. All right, there was no multiplication in this problem. But say, for example, I multiplied this top equation by 3. What would happen to the delta H?
We multiply by 3.
It would be multiplied by 3, exactly. So that's the main point of these, right? Sometimes you'll have to do multiple things to the same equation, like you have to flip and multiply. Keep track of like what you need to do and don't get lost.
So if the delta H of the second equation equals -178.3 due to the carbon dioxide and CaO being combined, wouldn't the delta H decrease if you take away CaO?
Delta H decrease. Here's the thing.
Like you're canceling them out.
Not exactly. So delta H is what we call a thermodynamic parameter. It only depends on the reactants in the products. But that's not a thing for this class. When you take Gen Chem 2, you'll learn more about that.
Price tables?
It's sort of related, like Le Chatelier's principle. All right, any other questions? All right, practice these Hess's law equations, get good at them. We'll do some harder ones Monday. See y'all later. Peace out. Yeah. Okay, so is the amount of heat released per the amount of heat absorbed or released overall. Delta H is the amount of heat released per mole.
Oh, so it's.
Yeah.
Oh, yeah, because it's just Q divided by.
Oh, yeah, no, you can.
Although on the test, we have to tell the different pictures to be able to solve like. The big capacity and then just.
I mean, the way we did it here is pretty much how you need to do it on the test. So for a coffee cup, use your specific heat. Bottom, use your regular.
Wait, say that again, for coffee cup, you use.